Okay, continuing on, the equilibrium and the equilibrium constant, which is something we covered in the last video. Equilibrium is a state reached by a reaction when there is no net change. For a chemical reaction, this state is reached when the concentration of reactants are no longer changing. So that's equilibrium. For example, for the reaction y goes to x, if the reaction is at equilibrium, then the change in concentration of y equals to the change in concentration of x, which will equal to 0, meaning that there is no change in those concentrations. So the reaction is at equilibrium at this point. So if we wanted to show this, it would be y goes to x, but if we're going to show it with a double arrow, y goes to x equals to x goes to y. At equilibrium, the reaction is proceeding both directions at the same rate. So equilibrium doesn't mean a state where nothing is happening. It just means that the reaction is proceeding in the forward direction at the same rate that it's proceeding in the reverse reaction. And that's why the concentrations don't change. At equilibrium, the ratio of product over reactant is the equilibrium constant. When you are at equilibrium, this is important. It's not just the ratio of product over reactant at any one time, but while at equilibrium, the ratio of product over reactant is the equilibrium constant K. Example, for the reaction y goes to x, when the reaction is at equilibrium, the equilibrium constant equals to K equals to the concentration of x, the product, over y. Note, at equilibrium, the equation for free energy of change becomes the following. So here's our equation that we're starting out with, but at equilibrium, delta G, at equilibrium, delta G equals to 0. And we're plugging that in here. So our equation becomes this, but also at equilibrium, the concentration of product, in this case x, over y, our reactant, equals to the equilibrium constant, K. Thus, if delta G standard is known, then K can be found, and if K is known, delta G standard can be found. And that is because we have two unknowns, and as long as we know one, we can figure out the other. The equilibrium constant, as with delta G standard, is unique to a chemical reaction and cannot be changed. So what are we saying here? The delta G standard and the equilibrium constant, K, those numbers are going to be unique to a reaction. They cannot be changed. So every reaction will have a unique equilibrium constant and a unique delta G standard, which is the property of that reaction. Now, this is both for physical and chemical reactions. And those numbers cannot be changed. If you change the conditions, you're only changing delta G. Just to make sure that we're on the same page, let's write our equation out again. Delta G equals to delta G standard plus 5.9 log of concentration of product over concentration of reactant, right? So the number that cannot change is delta G standard, and if you know delta G standard, as we've shown above, you can figure out the equilibrium constant. Or if you know the equilibrium constant, as we've shown above, you can figure out delta G standard. So the delta G standard doesn't change, but if I change the concentration of product or reactant, or this ratio between the concentration of product and reactant, what I will do is change delta G. I will not affect delta G standard. And we're not worried about temperature and pressure, since those are constants in a biological system. So those are not important to us. If a chemical reaction has a delta G standard less than 0, then its K is larger than 1 and is said to be a favorable reaction. Favorable as in at equilibrium, there's more product than reactant. So that's our definition of a favorable reaction. When we say reaction is favorable, we mean that at equilibrium, you will have more product than reactant. If a chemical reaction has a delta G standard larger than 0, then it has a K less than 1 and is said to be unfavorable. Unfavorable as in at equilibrium, there's more reactant than product. And that's what we mean by unfavorable. In both cases, and as we saw before, equilibrium is the point of highest disorder. So we had this picture from the previous video, example reaction, which had a K equals to 10 right here, right? And we said, okay, the reaction, if I have 1-to-1 ratio of reactant, which I'm showing here, or if I had 100-to-1, in both cases, the reaction will move towards equilibrium spontaneously, meaning that there is no need for input of energy. Moving from either one toward equilibrium will have a negative delta G. Again, not a negative delta G standard, a negative delta G. So if I want to go in the opposite direction, this way and this way, I will have to put in energy. It will have a positive delta G. And every reaction will have an equilibrium constant associated with it. And you can't mess with that. That is the equilibrium state for that reaction. And of course, if you know the equilibrium constant, you know the delta G standard. And if you know the delta G standard, you know the equilibrium constant. Okay, so we'll stop here for this video and continue with this example in the next video. All right, thank you guys.